So a brief introduction of who I am. Like I said, I'm with Intel's Open Source Technology Center, and my role there is team lead for the team that is porting Android onto the Medfield tablet reference design. So I've been working with Intel since March of last year. So I'm fairly new to Intel. And what I did before that, my experience with Android, a little bit of background. I worked for Garmin, starting with Android 0.9. And a lot of what I did there was actually doing apps and services to enable Garmin's legacy code base to run on Android, which was a challenge in and of itself. But most of my experience is probably a little bit unique among the presenters here, that I'm not coming from a strong Linux background. I'm actually more of an Android user space guy with a lot more experience in applications and services. So hopefully I'll bring kind of a unique perspective to this talk for you. So a bit about my team and Intel's Android board support package. We have a globally distributed engineering team developing the BSPs. We have offices in Finland, Romania, Oregon is where I'm based out of, and we also work closely with other Intel sites in the States. We also have what we call a distribution team, and this team is the team that handles infrastructure, source code management. We use Jenkins build servers, and so they set that up and do some automated testing as well. And so we're responsible for delivering an Android reference OS for the Intel Medfield tablet reference design. One thing, since I mentioned it later in the slides, I wanted to explain that we actually use a provisioning OS called Droid Boot, and that's actually our implementation of the Fastboot protocol. So our goals for ICS, basically we were challenged to try and get onto Ice Cream Sandwich kind of as quickly as possible. They told me days, not weeks. We were previously working with Honeycomb and decided that we wanted to move towards Ice Cream Sandwich. That was our best opportunity for success on tablets, and we didn't want to have this downtime where Ice Cream Sandwich was released and we were not able to get developers working on it. So we put a lot of planning into how we can accelerate the process of porting Ice Cream Sandwich to Intel's architecture. Obviously the goal is we want to get to market very quickly on Ice Cream Sandwich. A little bit of an overview of the talk. I'll be talking about the phases that we set out to bring up. During the planning phase, we really wanted to find some way to judge our progress and set milestones with kind of clear entry and exit criteria to make sure that we were on track to meet our goal. I'll also go over some of the key places to look when first bringing up Android. What we did by way of cleanup once we were done with the initial bring up phase, cleaning up some of the stuff that we did before bringing it back into our mainline development tree. I'll go over some of the lessons learned throughout this process, and then for questions, honestly, I prefer it if this is more of an interactive dialogue, so please feel free to raise your hand if you have a question anytime during the talk, and we can discuss it then. So this is how we broke down the different phases of work. The pre-work phase was probably one of the most critical phases. Obviously, Ice Cream Sandwich is developed using a 3.0 kernel, so there was some work getting the kernel running on our platform first. There was also some distro team or distribution team preparation. Basically, we wanted to make sure that we were completely set up so that when the source code was released, we could actually pull it in and deliver it out to the developers as rapidly as possible. One other piece of the pre-work was a deep analysis of all of the patches that we had on top of Honeycomb to try and determine its relevance going forward. There was also some logistical prep, like I mentioned. We had a geographically distributed team, and what we tried to do is bring everybody into the same room so that we were all working closely together. The next phase, so I'll talk about the exit criteria of the pre-work phase. Basically, the goal was, at the end of the pre-work phase, we wanted to have Honeycomb running on our 3.0 kernel and running pretty well. So the next phase was obviously when source code was made available from Google. That's when our distribution team implements the pre-work plan. The first priority of this particular phase is just building compilation, getting the code out to developers, and then starting our gap analysis. Obviously with Ice Cream Sandwich, there was a lot of change from previous generations. A little bit less so going from Honeycomb to Ice Cream Sandwich versus Gingerbread to Ice Cream Sandwich. But particularly in graphics, the USB gadget, there was some significant changes. So once we had the code, we wanted to start the gap analysis. And one of the exit criteria for this phase was actually setting up a nightly build. So we use Jenkins build servers to do build verifications. And so setting up a nightly build allows us to make sure that we're not doing things to regress. The next phase that we had outlined was the kernel bring up. So the goal here is being able to boot to the kernel command line with some stability there as well. And you also need the important tools to allow you to debug and flash at this point. So exit criteria for this phase was having ADB working, having Droid boot or provisioning OS up and running so that we're able to flash images successfully. And then, once you have a stable kernel, next goal obviously is booting to a UI. Our plan was basically to bring up the UI using the software rendering path first, while the graphics team had some time to bring up the hardware UI. So once we were able to boot to UI successfully and somewhat stably, we moved on to what I call a core OS bring up. So this is where once you have a UI, it enables you to go in and make sure the touchscreen is working. We can do some work to check on RenderScript, Dalvik, and some of the other major subsystems of Android. So at the end of this phase, maybe there's some apps that have issues, but you can launch to the home screen and system server doesn't die immediately. So there's some stability at this phase. And then once that's done, the core app bring up phase is where some of the peripheral subsystems, Wi-Fi, Bluetooth, sensors, where those are brought up. And so for us, the measure of success at the end of this project was that we had a functioning version of Ice Cream Sandwich running on an Enfield tablet. We had a nightly build set up, and we used Windrover's FAST system for automated testing. So that was another byproduct of this phase, is that we set up the automated testing to detect functional regressions in our code. A bit more detail on the pre-work phase. Obviously, Ice Cream Sandwich is on a 3.0 kernel, and we were previously on 2.6.3.6. So we knew it was going to be very, very key to have a 3.0 kernel functional on our platform before Ice Cream Sandwich was delivered. So in order to facilitate this, we used Honeycomb as kind of a preparation vehicle. So during this phase, which is about a month before the code was released by Google, we did a lot of work to verify the 3.0 kernel using Honeycomb as that testing vehicle. So another component of the pre-work phase, all of our patches for AOSP projects were analyzed, and we put them into buckets. Basically, the goal here was to develop a toolbox we could pull from as we were moving from Honeycomb to Ice Cream Sandwich. We didn't want to simply take what we had on Honeycomb and rebase it without being pretty deliberate in that process. So the emphasis was really to minimize the number of changes we needed to bring forward and carry forward to the new version of Android. As many of you are probably well aware, there's definitely a cost to going in and modifying some of the core pieces of code. So we're trying to minimize that cost to make sure that everything we brought forward was absolutely necessary and absolutely relevant. So for all the patches that we had, we went and put them into buckets of don't port, maybe port, for port. And this is what we used later once code was delivered to us to figure out what needed to be brought forward. A little bit about our infrastructure plan. Like I said earlier, developing ways to rapidly bring the source code into your network and also deliver it out to the developers that are working on the code can greatly speed this up. So what we did is we set up an ICS branch initially pointed to Honeycomb and an ICS branch in the manifest project, and this would allow us to later, we already have a manifest created, we already have all the ICS branches created, so we could very easily go in and repoint them later. And part of how we made that repointing a little bit easier too was developing scripts, not only to very easily and rapidly add a large number of mirrors into our system at one time, but also to repoint a large number of branches all at one time. So we actually use a mirroring infrastructure based on YAML. So we have a markup language file that describes all the mirrors, and so what our scripts would do and say, okay, well, if I have a Honeycomb branch in this particular project that we're mirroring, we're going to go and add this branch also. So when the code arrived, we were very, very fortunate to be able to rapidly add mirrors and pull everything into our infrastructure. So, very, very long day. When Ice Cream Sandwich was released, we immediately put our infrastructure plan into effect, and the mirrors were up within 1 hour. And one of the first places we looked before the mirroring was even done was in the Manifest project. So that's definitely a key place to look when you're moving from one version to the next. In Honeycomb, even maintenance releases, they were adding projects and deprecating projects, and the Manifest is one of the easiest ways to figure out what they've done. So, for instance, we were able to determine that they'd added a tiny ALSA component in Ice Cream Sandwich by inspecting the Manifest. So we were able to add mirrors for new projects and delete mirrors for any projects that were no longer being carried forward. So another key for code distribution, one of the things that we found was that having 20 or so developers all creating fresh repos using multi-threaded repo sync all at the same time trying to pull down the information was kind of a performance drag on our server. So one of the suggestions for the future to make this a bit easier is have 1 or 2 people do it, pull it down very quickly, and then copy the .repo directory, which actually contains all the .git directories for each project. And then you copy that onto a USB stick or something, and you can distribute it out to developers that way. That would be a very significant time savings, I think. So one other thing we did at this point, I'll get into it a little bit more later, is that for the bring up period, which again was supposed to last days, not weeks, we created a temp branch so that we could keep track of all the work that we did during the bring up. But it would allow us to maintain that history when we move back to our mainline development. We don't necessarily have to keep all the hacks and workarounds and some of the nasty stuff we did just to get things booting. We didn't have to put that on our main branch. So having a temp branch made it easier for us to clean up the system later. So early tasks, fixing the build. Once we had code out to all the developers' computers, obviously first order business is to successfully build. So how do you efficiently parallelize this task? What we did is we had one person who was using make-k and identifying all the build errors that we had. So make-k, you can proceed through all the different build failures and enumerate them. And once one was assigned, yeah, go ahead.
I've never seen the minus K option on make. What does that do?
Basically what it means is don't stop on an error.
Okay.
So, you know, if you're building in serial, it's inherently going to be difficult to parallelize. So using -K allowed us to kind of collect a list of all the build errors that were encountered. Some of them obviously are going to be caused by previous build errors, so it's you know, a little bit of a black art, I suppose. But it did allow us to move forward in parallel and assign multiple developers at the same time to go and address build issues. And obviously communication is very, very critical at this phase, making sure that we're constantly talking with each other. Like I said, we were using a whiteboard to track everything so that everybody could see what was going on up on the whiteboard. And so, you know, when a build error was encountered, the engineer really had 2 options. We could either temporarily work around the issue or we do a proper fix. And you know, preferably we would find a way to do a proper fix. But obviously, with the goal of trying to get the system booting and functional very, very rapidly, you don't always have time to go in and do the correct fix. And so if it was a non-critical component, one of the options is to just not compile it and deal with it later. One thing we did take care to do, though, is whenever we did have a workaround and not a proper fix, is we would track it in our bug system, make sure we didn't lose track of it later.
So,
Yes?
how many errors did you find?
Oh, I don't know that I have the exact number, but it was in the teens, I believe. So like I mentioned, some components were simply excluded. Height map profiler, for instance, one of the things we do in our internal builds is we actually build the compatibility definition document required apps, the sample apps that are up on apps for Android. And you know, one of those was causing a build failure, so obviously that's non-essential to our success of booting to a UI, so we just excluded it, logged the bug, and moved on. And then others were quickly fixed, pushed to Git. Another one of the very first steps that we had to do was actually port build patches. So, you know, with Intel, we're building for x86. There are some changes that we have that are not accepted by Google yet. So, and we also do an in-tree kernel build. So part of the build for all developers is actually a full kernel build. And there's a series of patches and builds to allow that. And so the ones that we had in our list, we went back to our toolkit from our patch analysis before, and the ones that we were must port, this is where we immediately went and brought those forward. One thing to note is while we could have just given push rights so that people could push directly up to our server, we decided to still use Garrett. And one of the thoughts with that is that could potentially be something that would slow you down. We thought it was probably worth the risk to go ahead and use Garrett anyways, because we still felt like, especially when you're moving quickly, having somebody go in and quickly verify your work and code review was still pretty important. The standards were certainly a little bit lower, but we still wanted to make sure that we were reviewing things. We did actually catch things in review during this time, so I think it was definitely beneficial to go that route rather than just direct pushing. Plus, it's a little bit more controlled. And so, basically, we were able to get our build successful within a few hours of source code availability. Oregon time, I think the source was released 3:30 p.m. Or so, and we had it building by about 7 or 7:30. Next step, getting through the boot. This is really where the pre-work that we did using Honeycomb for our 3.0 kernel, it really paid off. With minimal changes to the init scripts, we were able to get our kernel booting and stable using Ice Cream Sandwich. So while we're talking about init, I figured I would kind of go over some of the Android init because it is a little bit different than what you might experience in a typical Linux system. The Android init language is basically a way to associate a series of commands with a particular trigger. So you have all these different action triggers, early init, early FS. This is actually the order in which they're executed by init. And so at each one of these phases, there are different things happening. One of the gotchas that I like to point out, because this is something that we see kind of again and again, is in the init scripts, if you're trying to access the data partition, you have to do it in post-FS data or later. It may actually work earlier on, but if you have data encryption enabled on your tablet, you will get bitten by that. One other thing you can do in the init system that's actually pretty cool is the property changes. So the ADB daemon is a classic example of that. This is a service that is initially declared as disabled, but there's an on property changes event for debuggable, and when that gets set to true, the ADB daemon starts up. But this is also a very key place when you're bringing things up, to be able to go in and disable certain things. So, for instance, when we're trying to verify our kernel and boot in the absence of the Android UI, the easiest way to do that is just to go in there and disable the Zygote service in the init scripts. And the way you do that is basically in the service description. You declare a service, and then there's some modifier options that appear down below that, and adding disable to the modifiers of that service will make it not start. One other one that's very helpful during this particular phase is if you have a service that's crashing over and over and over again, you can modify it with the one-shot modifier, and that one basically means that if my service crashes, I'm not going to try and restart it. Okay, some of the runtime errors we encountered. So once we took the disabled modifier out of our Zygote, we noticed that the system server was failing to start and crashing over and over and over again. And so this is basically, the system server is the component that really is kind of the backbone of the Android user space. And what it does is it will go in when it starts and start all of the Java services that are available to applications. In certain cases, with core services, it would be very difficult to do this. So if your activity manager is crashing, the only option really is to go in there and solve the problem. But for us, what we saw was that it was actually the NFC service that was repeatedly taking down the system server and causing Zygote to start over and over and over again. NFC was kind of deemed non-critical to our ability to bring this up. So what we did is we just went into comments out at the start of the NFC service. So where you do this, here's the name of the file in systemserver.java, and basically there's just a very long list of all the different Java services in there, and comment them out and move forward. So that's what we did to get past that particular runtime error. Other ones that we encountered, and very common ones when you're bringing up new hardware, is sound. So in Android 4.0, I mentioned earlier, TinyElsa was introduced as the audio HAL. And for Honeycomb, we had actually been carrying forward the ALSA sound module that was actually deprecated in Honeycomb MR2. And so we've been carrying it forward. And at this point, this is one of those places where instead of simply carrying forward the old way of doing things and using ALSA sound, because that's what we did on Honeycomb, we decided to move forward and change to use TinyElsa. But obviously that's more of a longer term thing, and it's not imperative to get the device up and running. So we did a workaround basically to use the generic Android sound HAL and a dummy kernel sound card. And so how you can do that is in your board config.make. Board uses generic audio as a build variable. You can set to true, and then kernel config option to use a dummy sound card. And there's a very similar logic you can do for camera stub. Obviously, ICS had a whole lot of camera changes, and we were not ready for that. So we just used the camera stub in order to get past some of the camera errors we encountered. So, booting to UI, very, very important step in bringing up Ice Cream Sandwich. Our hardware graphics were not usable at first. So a temporary solution was needed to unblock a lot of the work that really depends on a UI. I mentioned earlier, touchscreen is something that really would like a UI to be able to test. And so Android has a software rendering path that you can enable to enable the UI to actually come up in the absence of full hardware accelerated rendering. So the component that does this is called Pixel Flanger. And so you can change your EGL config to remove PVR or whatever graphics chip you're using from screen 0, and then remove all the PowerVR libraries from product packages, and if you're doing an incremental build, you also need to clean them from your out directory. And then we also modified the Grellet frame buffer to hard code the screen dimensions there. And really having a functional, albeit slow, software rendering UI brought to our attention that we had problems with our touchscreen. And it also unblocked a lot of the other UI-dependent tasks. For instance, testing Wi-Fi becomes a lot easier once you have the UI to go in there and enable and connect to an AP and do some testing on how it's working. So this is where we were. We were able to boot to UI using the software rendering path. Unfortunately, system UI has stopped. That was actually, I believe, caused by the NFC server crash. It would just kind of happen over and over again. So a little bit about hardware versus software UI rendering. Ever since the very beginning, window compositing was done with hardware acceleration, but not the actual content drawing. And that changed in Honeycomb because as you increase the resolution of the screens, doing the software rendering really does become a pretty significant bottleneck. And for tablets, it's one of those things where the performance is pretty unacceptable. So Honeycomb introduced the hardware accelerated UI rendering, but applications would have to opt in to hardware accelerated rendering. What they found is that a lot of applications would crash or have problems if hardware rendering was enabled. So it was not enabled by default in Honeycomb. Now that all changed with Ice Cream Sandwich, where hardware rendering is enabled by default. So in order to turn that off, there's another build variable, use OpenGL renderer, and you can just set that to false to disable hardware accelerated UI rendering. So, like I mentioned before, hardware UI rendering, there's special support required from EGL. And so, while our graphics team was trying to sort out how to integrate the PBR stuff with the Android graphics stack, being able to boot using the software rendering path really did help us resolve a lot of issues that are only visible in the presence of a functional UI. So we actually had this 3-hour window. Luckily, we have a very good graphics team. They were able to figure that out very quickly. So we had software rendering up, and 3 hours later we had hardware rendering up. But in that 3-hour period, we were able to make forward progress on a lot of other issues. So by the time we actually had the hardware rendering up, we had a fairly stable system where Wi-Fi was working. We were able to use many of the apps, and a lot of the peripheral system sensors were functional at this point too. So a lot of that stuff was really made possible earlier on because we had decided to enable the software rendering path first. So I got a little video, to prove it. I think this is actually going to come out.
No, it's still DB1 running
So one of the things I'll mention is that we have these very early orange pumpkin jack-o'-lantern looking tablets. I invite you all to go out to the Intel booth after this talk. You can go and play around with the form factor of the Medfield tablet reference design. It's running ICS right now. We're on ICS MR1. So go take a look and check it out. I like it. So some of the key places to look. I've mentioned touchscreen before. When we were using Honeycomb's preparation vehicle, Honeycomb was expecting touchscreen protocol A, and the upstream driver we were using for our touchscreen was actually using protocol B, and so it didn't work. That touchscreen didn't work initially on Honeycomb because of that. So we wouldn't change the driver to go and report to touchscreen protocol A. And then ICS comes out, and touchscreen doesn't work again. We find, well, because ICS is actually now expecting protocol B, so we had to go in and revert that work. And then one other note about touchscreens is that touchscreen is mandatory to use an input device configuration file. And I've kind of pasted the bare bones implementation of what you need to actually get a touchscreen recognized on Android. There are a lot more properties available, and what I would recommend is discussing with your touchscreen vendor ways to optimize those properties, because they do have an effect on the behavior of the touchscreen, and by fine-tuning a lot of those properties, you can get much better touchscreen behavior. Another thing that changed, particularly for those who are coming from gingerbread ice cream sandwich, is that in Honeycomb MR2, they introduced this new way of managing storage volumes. So previously on Android, there wasn't really any built-in way to support an internal storage drive very well. And so that's been, and it's still not particularly wonderful now. There's still some work to be done, but there is actually a way to register it on the system. And so the mechanism to enable that, starting with Android 3.2, is this storage list.xml file where you can define all the volumes on your system. And then they also introduced a few other components. So one of them is the Fuse file system. That's one where you can mount an ext2 or ext3 partition as a FAT32 partition. And so with a combination of using the Fuse file system and this new daemon called SD card daemon, that will actually mount an internal storage volume at your SD card mount point. So some of the options related to that, I posted, this is actually the storage list that we're using on the tablet right now. Storage description is a string that would appear in settings once this drive is mounted. So that would allow you to customize the name. For instance, we're using a USB mount point as well, so you could actually mount a USB stick and support it directly. We also have an external SD card. So some of these values here, the primary is really the primary external storage variable that you also define in board config.main. It's not very aptly named, and it confuses a lot of people because our primary external storage is actually an internal storage partition. But that's kind of a legacy name. and so you can denote that it's the primary storage volume there. Emulated means that this is a volume that is controlled by the fuse and SD card daemon mechanism. So it's an emulated storage partition. The MTP reserve is something that allows you to withhold a certain amount of space from the MTP service. So in our case, 500 megabytes are restricted from MTP, so MTP can't actually consume the entire storage volume. I think I don't remember everything else there. So, oh yeah, removable, true for the SD card and USB card. More key places to look. Android configuration and the device overlay are very important places to look when you're bringing it up. Particularly, Ice Cream Sandwich introduced a whole lot of new configuration options, and many Android properties are controlled through that file that I point to right there. Right there, the config.xml file. So some of the examples of things that are controlled through that file are tethering behavior, tethering regexes, networking configuration, animations, UI behavior, icons, vibrator patterns for certain actions that happen in the system. And when you long press the power button, what UI shows up and how it behaves, that's controlled by config.xml. So if you haven't yet, I would urge you to go ahead and look through that whole file and see all the things, all the points of configuration and customization that can be achieved through that mechanism. The reason why I'm discussing device overlays here is because you don't want to go in and muck with frameworks. Applying patches on top of frameworks can get a little bit nasty, particularly when you're doing a major version upgrade, because a lot of the resources will change from upstream. So there's actually a really cool mechanism that Android has in place to manage this, and it allows you to override any of the resources that exist in framework space or in packages apps. So you can override pretty much anything, any of the Java resources that get compiled. And the way it works is you basically have a parallel file system hierarchy, and you'd have an overlay directory that has framework space, core, res values, config.xml. And in that overlay directory, you'd have not the entire file, but you'd have an XML file containing only the elements that you wish to override with that overlay. So if there's only 3 things that you want to override from the default behavior of framework space, you'd only have 3 things listed in that overlay file. And it's the same thing for packages apps. So you'd have an overlay directory with packages, apps, launcher 2, whatever you want to do. And there's actually 2 different layers of the overlay. The first one is the device package overlay, and the second one is the product package overlay. And the idea here is you might have a set of common options that you want to apply to a particular device, but you also have some specialization for particular SKUs of that device. So you may want to have one configuration for a product where tethering was disabled, for instance, or you needed to change the default locale. That's stuff that you could do in a product package overlay, because how it works when it's compiling resources, it would first start out at the frameworks or the apps level, and it would parse that XML file, determine the options, then it would apply the device package overlay, and then it would apply the product package overlay. So if you wanted to, you could actually override something that was in the device package overlay with the product package overlay. So like I mentioned before, this is really used to replace or override any framework or app resource. A couple of the ones that I think are particularly pertinent to customization and bringing up a new system. The first one there is the settings provider. So for a majority of the settings that are available on Android, not all of them, but for a majority of them, you can actually set the default value by overriding resources that they've defined in their defaults.xml. Similarly, the system UI has a whole lot of tunable parameters in another config.xml file that you can override. Here's an example for an app. You can add an overlay to override some of the variables in Launcher 2. And Launcher 2 is the home screen, and one of the reasons why I bring this up is because we discovered that AOSP, not AOSP, it's Honeycomb, so it's not really AO, from Google, the launcher actually didn't work. And it turned out that the reason why it didn't work is because Google's own internal repository, they actually had an overlay applied, so they didn't even notice that it didn't work. But they were expecting that a particular value in the launcher config.xml file was actually going to be overridden. And so that was a challenge to find. There's an example of Samsung using an overlay in AOSP. If you want to go and check it out, it's in the device Samsung Tuna overlay. And you can kind of see their approach to what they've done to customize Android using this mechanism. More key places to look. This isn't really key necessarily to a bring up, but I've attended some of the other talks this week that have seemed fairly similar to what I've discussed, and this is one thing that has not been brought up. This is something that you wouldn't catch later on when you went to get certification, but it's good to know about it now. CTS, the compatibility test suite. So the package manager actually looks at these product capabilities that you can define for your platform to perform market filtering. So, for instance, if an app requires GPS, they would say in their manifest, use this feature, Android hardware location.gps. And if your platform doesn't define it, that app will not show up in the market. So that can definitely cause some confusion if you go in there and try and find some apps. The CTS tests do try to verify that what you actually have available on the system is properly declared. I don't know that it actually catches everything. So it's good to be aware of this. These files are in framework space, core, data, etc. And basically all you have to do is move them to, I believe it's system data etc. As part of your product copy files. And that's basically how you declare support for a particular feature that's available on the Android. One other thing that can cause some problems if you're not aware of it, I don't think this is very well documented anywhere that I've seen, but the RO.SF LCD density is really a virtual screen density. So if you go in and actually calculate the correct screen density for your platform, you probably don't want to use it because it expects, the system expects that this value is one of a discrete set. And that set is what I've enumerated here. So they have a density low devices, density medium, so on and so forth. You're not restricted to actually select whichever one is closest to your screen density. And one of the things you can actually do to play around is literally just set it to different things and see what works best on your device. So you may be between two of them, and I would suggest experimenting to see which one works best. Now, I've heard rumors, and don't hold me to this, that they're actually going to allow you to dynamically change the device density to be able to kind of zoom in and out. I don't know when that's coming, but I've heard rumors that that's kind of a skunkworks project. Other key places to look. When you're bringing things up, power management, you don't want that to be causing problems. Basically, you just want to exclude it as a potential source of issues. So the easiest way to disable it is in your initRC. Just go ahead and grab a wake lock, and that'll keep the system from going to suspend and make sure that when you're encountering issues, you know they're not related to power management. Obviously, this is one you want to disable relatively soon afterwards and make sure that you're finding and solving all the power management bugs. But it can be helpful during an initial bring up just to get things going. One other suggestion is that while it's not required to have host mode working by the CDD, having it working is pretty helpful during this phase, because if your touchscreen is not working or if you're having trouble with it, you can use a keyboard and mouse, starting with ICS. Well, actually starting with Honeycomb. One other thing we can do, this is maybe a little bit particular to Intel. The Dalvik virtual machine will pretty much work out of the box as delivered from Google for ARM platforms. For us, we found that we had some problems with the x86 virtual machine. So you can either set it dynamically at runtime. So here's a command to be able to set that. You can also do this at build time by setting a system property. Basically, it's the same system property named alvic.vm.execution mode, and switch to the portable interpreter. That one is pretty solid and pretty much guaranteed to work. So if you're running into Dalvik issues, that is one potential solution to try, is just using the portable mode of the VM. So other key places to look for hardware UI rendering, the hardware UI library, that's where surface texture is, and that's the key integration point for getting the hardware accelerated UI rendering functional. And one other thing that we noticed was Android Strictmode, and I'm actually not entirely sure when Strictmode was introduced, but it was gingerbread. Okay, it's I don't know if it was actually honeycomb. Maybe that's why it was a surprise to us. But it's a very useful thing. Will tell you if your app is behaving badly. For instance, if you're doing something on your app's main thread that's taking a long time and would generate an application not responding error, Strictmode will basically, in a very, very verbose manner, inform you of it in logcat. And what it dumps out are call stacks. So, you know, we're in the middle of the night looking through the logs, trying to figure out what's going on, and we're seeing a whole bunch of call stacks. And that was a little disconcerting until we realized that they were really just warnings. But like I said, it's a very, very verbose component. And when you're bringing things up, things are going to run slowly, and you're going to have things that are hanging on the main thread, even if it's not a real problem. So you may want to go ahead and disable that just to clean up your logs and make it a little bit easier to find what the real root of the problem is. So it turns out there is a system property you can set to disable that, and the persist.sys strictmode.disable equals true in system.prop will go ahead and disable strict mode for you and make it a bit easier to sift through your logs. Okay, so some of the cleaning up that we did, like I mentioned before, we used a temporary branch, and the real value of this is that we wanted to be able to maintain the history of the problems we encountered during the bring up and the approaches we took to solve them. But having a lot of that information in the Git history, we weren't really sure we wanted to release all that to our customers. You know, our product is a BSP. And part of that product, a valuable part of that product, in my opinion, is the Git history for each project. So being able to clean up and remove must revert and revert pairs, and making sure commit messages were up to our standards, and cleaning up other things and removing hacks was something that we did when we were moving and cleaning up from our temp branch and pulling that back into our mainline branch. So it allowed us to keep the history on the one hand, so that the next time we're doing a bring up, we can kind of see what was done in the past, but we could also clean up our history. So we selectively cherry picked changes from the bring up branch and brought them back over to master. So the lifespan of the temp branch was about 48 hours. It's all kind of a blur when this happened, but I'm pretty sure it was a Monday when an ice cream sandwich was released. And by Wednesday, everything was back in our mainline branch, and we were able to get the whole team started on ice cream sandwich development. So it was definitely critical for us to be able to reach our goals as a team. So some of the lessons learned from all of this. Really, this is honestly probably the biggest point I can make, is having the right expertise was absolutely critical. Like I mentioned before, I'm a little bit higher up the stack than most of the other members of my team. And having a team that's very strong on Linux fundamentals, and having a team that was very strong with Power VR was absolutely critical to our success. Without the right people, without their knowledge and help, we never would have been able to get it done. One other thing we judged very valuable was the co-location. So we brought team members from Romania in. We had intended to bring team members from other groups in. As you well know, Google is not necessarily forthcoming with schedules. So that can be kind of difficult to plan, to make sure that we get everybody in the same room. Just so happens we got lucky and we were able to have some of the Romanian team members in the room. But if you can't have co-location, certainly have a common chat room where you can do real-time communication. Email is just too slow. So we were constantly on our IRC channel and talking to each other constantly. And one other thing we did is that we basically put a hold on our engineers, and no managers allowed, no meetings allowed. They were quarantined basically, and there were no meetings being attended except for very short ad hoc engineering huddles as needed. And this was critical to making sure that we were all on the same page, that we were able to collaborate and solve some of the problems together, and as kind of a checkpoint just to make sure that everybody was making progress. And then the other lesson learned, I would say, is always maintain focus on how to parallelize and how to unblock people. Enabling the software rendering path was deliberate. We knew that we'd be able to do that quickly, and we knew that would unblock and allow for parallel progress on a lot of different areas. And whenever you encounter a problem, trying to look at it from the way of, how can I work around this to help unblock other people, can really help you make forward progress in a parallel fashion.